Hi there, YouTube viewers. I'm going to do a quick video on my 3-point hitch project. To give you a quick update, I've got my cylinder mounted and I'm setting up my geometry for the crank mechanism that's going to be on the what they refer to as the rock shaft for the 3-point hitch. So basically it's a linear actuator, which would be a hydraulic cylinder that rotates a rock shaft. So essentially it's a bell crank. So you've got two fixed pivot points. There'd be the pivot point for your cylinder, and then the shaft center for the rock shaft, and those are established in space based off of the hard points on the tractor. So these are actually casting features in the tractor. In this case, it's a mounting flange for a bracket, which I've built, that has a box bracket with a pinhole in it. And then there's two casting loops that are in the tractor itself with some bronze bushings that would be the center line for the rock shaft. So ideally what happens is, you've got linear motion and you're going to convert it into rotary motion through hydraulic power. Now the tricky part about setting up this geometry is that this all packages underneath of a floorboard. It's basically kind of split between the axle casting on the bottom side and a floorboard that's on the top side. So there's the sheet metal running board that goes up here. So this setup will actually, it's not going to be fixed in space, so if this is my cylinder and this is my pivot point, it's actually not just going to move in and out and then twist an arm. It actually rolls through a little bit of an angle here, right? And that's the nature of the bell crank geometry. Because normally some of these, in a vertical mounting scheme, that's not usually a big deal because it's just kind of hung out there in the open. But because this has to package in kind of a narrow space, I plotted it out on some paper just to make sure I wasn't going to have any issues with it. So the cylinder, I guess the key parameters here are the length of your cylinder, the fully extended and fully retracted length of your cylinder, the amount of workable stroke you get out of your cylinder, and the crank arm. So the radius between the pivot point and where it attaches to the end point of the cylinder are all pretty critical. So by selecting particular cylinder geometries and having some adjustment on them, luckily these tie rod cylinders usually have quite a bit of adjustment on the threaded end, on the rod end, because it's just a clevis that goes onto a big screw. You can get quite a bit of, I'd say, free length adjustment to kind of fine tune this. And really the big thing here is this just shows an example. So if I think this is about an inch worth of tie rod adjustment on the end of the cylinder, you can really manipulate the overall length of this, or the resting position or retracted position length of where this pin is going to end up in space, right? So on the paper, I just established my hard point, which would be the pivot pin right there. I've established the measurement, the relative measurement for the center line of the rock shaft, and then I can kind of figure out what is my ideal geometry from a crank arm radius perspective, and where the overall cylinder length is going to be in the retracted position and then the extended position, and then kind of find that happy spot of how far back this needs to be rotated beyond center to make sure that I'm gonna work within that height difference that's gonna fit within the packaging space I have, right? So you can see on this example, if I were to have this cylinder pin start off at the base of the circle, it's going to actually rotate up probably even further than this. And you can see as you get towards the edge, as you get further out here, that height becomes pretty critical. You're going to actually roll that to a point where it's gonna see a significant amount of height change over that distance. And what that means at the pivot end is that you're going to rock this quite a bit, right? So in my case, I want this to have kind of a flat attitude. I don't want it to dip down too much, and I don't want to dip up too much within that 8 inches of stroke. So this is kind of how I worked it out. So how far back you start, you know, above the lowest point of rotation, or the base of the circle, how far back you start relative to where it's going to land is going to help you establish how much you'll say rock about the pivot point on the cylinder you have. Okay, so that's kind of how I worked that out. That's where I figured out how far back my pin was going to be when it's fully retracted, what kind of a realistic rocker crank arm I can you know reasonably work with, and that's really your, you know, that's your torque arm. So maximizing that is important, and then it also helps me establish, you know, if I start here and I end up over here, how much usable lift am I going to get out of this for the lift link geometry I have. So that's how I worked it all out, and I'll show you on the tractor kind of what it looks like. So you can understand the packaging problem I'm working with. So this is a 3-inch tie rod cylinder that's got an 8-inch stroke, and as I was mentioning, you can kind of see this is a, you know, it's about 2 fingers worth of clearance there, and a real similar story on the bottom, probably a little bit less on the bottom. So I've ended up with just under a 7-inch crank arm, which should it gives me enough room for this to freely operate without slamming into the casting or touching up against the bottom of the running board when it's in its full retracted and full extended position. And then all I have to do now is kind of get some firm up my dimensions on how much offset I want, so that cylinder stays in line with the pivot point, so it's not rocking outboard or inboard and looking goofy. I want that to stay straight, so I can establish where I want my reaction plates to be. So this pivot will actually be free floating around this bore. So this will actually just roll on the shaft itself. It's essentially just a reaction point, and it would be lifted by 2 of these sector plates, 1 on each side, that will get welded, fully welded to the rock shaft. And so this will actually do the lifting. And the cool part about this is it'll be a pin and double shear that I can just it's removable, and it allows you to rotate the relative position here by 15 degrees up and down. And that basically what that allows you to do is you can clock the relative positions of your lift links depending on whether you want to get more height or your starting point. It allows you to clock your starting point. So if my lift links are neutral, I can have them tilted 15 degrees down and they'll still roll up. And really what that means from a 3-point hitch geometry perspective is you can have these go like slammed into the ground, or you can actually have them lifted up a little bit. And really, I don't know if I need it, but the concept here is that if you're going to build something on your own, like a homebrew concept, build it adjustable. That's always the best practice. If you can't build it right, build it adjustable. Or if you can't build it perfect, build it adjustable. So that was my thought process there. So hopefully in about 2 weeks, I'm going to have some parts back from the machine shop. I'll get them thrown in here and probably do a little more elaborate video of the fitment process, the weld up, and then hopefully the installation, because I am going to have to take the wheel off again, which I'm not happy about, but it's not absolutely necessary to get this done. So until then, I wish you all well, and hope to hear and see from me again.